So I'll go ahead and give the introduction here. It is my great pleasure to introduce Mikyoung Lim as our speaker this morning. She's a professor at the Korea Advanced Institute of Science and Technology, KAIST. Quite some years back, she was on the faculty at Colorado State University. I have to point that out. So it's delightful to see you, albeit online. And she'll be speaking on analytic shape reconstruction of a planar conductivity inclusion. Okay,
thank you so much for inviting me and give a nice introduction. I'm very happy to share my recent result with you. Today's talk is about explicit shape recovery formula for simply connected conductivity inclusion in 2 dimensions. It's based on layer potential technique and geometric function theory in complex analysis. And omega is assumed to be simply connected bounded ellipsis domain in L2. And from the Riemann mapping theorem, there exists uniquely positive number gamma in a conformal mapping defined for exterior of omega, such that it extends infinity to infinity and psi prime at infinity equals to 1. And gamma is called the conformal radius of omega. And then psi admits the Lorentz-Weiss expansion. For W bigger than gamma has expansion, it has only one positive term, W, and the constant A0, and then negative order terms. And the coefficient is denoted by A sub n. And the problem I'm considering is very simple. It's a 2-dimensional transmission problem. Omega has constant conductivity sigma and exterior assumed to be of constant conductivity 1. And for given the entire harmonic function, let U be the transmission problem solution. And today I will give solution expression for U in terms of sigma, gamma, and AN. Also provide inverse problem solution. That means express sigma, gamma, and AN from the measurement of U. And the problem setup is simple, but I want to give explicit solution expression for the parameter sigma and the coefficient of psi. So main technique is layer potential method. The single layer potential and the Neumann-Poincaré operator is defined by the boundary integral, where gamma is the fundamental solution to the Laplacian. And since I'm interested in the 2-dimensional problem today, let's just fix D equals 2. And the solution U to the transmission solution has the solution expression. U equals to the background solution H plus single layer potential with the density function phi given by the solution to the boundary integral equation. That is lambda identity minus K star inverse with normal derivative of background potential H. Here lambda is given by conductivity value. So lambda is sigma plus 1 divided by 2 times sigma minus 1. Then from the layer potential formulation and just using the Taylor series expansion, the U minus H has this multiple expansion where you have summation with basis functions given by derivative of fundamental solution, and the alpha and beta multi-index. The M alpha beta depends on the domain and conductivity, and they call the generalized polarization tensors, I mean GPTs. And these GPTs the name came from the polarization tensor, which is the first order term of the generalized polarization tensor. So there, M is defined as boundary integral of the first order polynomial y sub j, and have lambda identity minus k inverse. And instead of a capital H, we put x sub I. So this corresponds to the cases alpha and beta of magnitude 1. And for higher order part, and small m alpha beta are defined in the same way, but with y of higher order. So beta and alpha are multi-index, and it just really generalizes the PT definition. And the values of GPTs can be obtained from the multi-static measurement data. So from now on, I assume that from the measurement, the GPT values are given. So the inverse problem I'm considering is to get the exterior comfort mapping psi from the given values of the GPTs. The polarization tensor of an ellipse is this diagonal matrix. When the ellipse is located at the center, it has a very simple formula. And in the general shaped case, an equivalent ellipse, that is an ellipse with the same PT, approximate the shape of omega, where the location is obtained by several more GPT values, but they're lower order terms. So this PT approximate the shape of omega. And higher order part give further details. So those two examples are obtained in collaboration with Professor Mikyoung and Eshelby and Garnier and my former student Yu, using optimization approaches, the GPT values with with higher order than the result, the obtained solution catch finer details of the shape. And by adopting level set framework, it works also for multi-connected case. In fact, by knowing all of the values of GPTs, we can uniquely determine the shape of inclusion and also the conductivity constant value. So my question is how to get how to use it higher order terms as well to have explicit shape, explicit formula for the coefficient of psi, so we get the shape of omega. In the ideal case that having GPT values for full order, then we can recover exactly the original shape of omega. Let me start with the easier case, that is extreme conductivity case. So this is work in collaboration with Professor Gang and Lee. And here, sigma is 0. So normal derivative of u is 0 on boundary of omega. And from now on, we identify x in L2 with complex z x1 plus ix2. Let capital U be a complex analytic function in the exterior of omega, such that real part of capital U equals to this solution U. Then from the boundary condition, imaginary part of U is constant on boundary omega. And this relation implies that the complement mapping function to the n, multiply n times of psi w minus summation gamma mn1, which is a linear combination of the GPT values, and divide by psi wm, then this function is an entire function. And that property gives us relation between complement mapping coefficient and the GPT values. So then expression of complement mapping coefficient in terms of GPTs or is derived. But since the entire function is quite complicated because it's a summation of functions, so the formula obtained here is not simple. I mean, it gives the exact value, but still needs to be still not an easy way to understand how this expression gives the coefficient of psi. And now let's think about for the arbitrary sigma case. And the information we have is m alpha beta, that is coefficient of this multipole expansion. So we know that u minus h, and h is background solution, is summation of this function where the basis functions are derivative of gamma, and we assume that m alpha beta is known. And this expansion holds x for the magnitude of x sufficiently large. So in general, the expansion doesn't hold near the boundary of omega. So in the general conductivity sigma case, it's difficult to derive relation for the GPTs from the transmission condition of U, differently from sigma equals to 0 case. So to overcome the difficulty, I take the following steps. Yeah, first, derive a series expansion for the layer potential operators using psi omega. So derive some geometric series expansion. And I will introduce the new concept of Faber polynomial polarization tensors. That's a modification of the classical GPTs. And then express formula using FPTs for the extreme conductivity case. And that is much simpler than the previous result. Then finally, generalize the formula to the arbitrary conductivity constant case. To do that, we need to define exterior coordinate. The exterior complement mapping, since it's conformal, it defines exterior orthogonal coordinate rho theta in the exterior region by W equals to exponential of rho plus psi theta, and the relation is Z equals to psi W. So you may understand it as modified polar coordinate. For the case omega is disk, then this coordinate is just a polar coordinate. And the figure shows that the level coordinate curves of rho theta are orthogonal. So from the conformality of psi gives this orthogonality for the coordinate. And since psi is conformal, the W to the plus or minus m, that is exponential of rho plus psi theta to the plus minus m, are harmonic function. Actually, real and imaginary parts are both harmonic functions. So using this exterior coordinate, we have exterior harmonic basis. And for the interior basis, I had a difficulty for a while to figure out the interior basis. My initial idea is to use interior complement mapping, but then there is no explicit way to deal with the transmission condition. And then the Eshelby conjecture gave me an idea. So let me review the Eshelby conjecture. The Eshelby in 1957 discovered that an ellipse embedded in an infinite elastic medium induces a uniform interior strain for uniform loading. And the Eshelby conjecture is that amongst closed surfaces, the ellipsoid alone has this convenient property. So if you see the figure, for omega an ellipse, then applied capital H is first order polynomial. Then the solution U is perturbed function. Inside the ellipse, it is first order polynomial. So even though exterior function has decaying solutions as well, but inside omega, so we just need a polynomial function. So real and imaginary part of polynomial actually form an interior harmonic basis. So we don't need to use interior component mapping as to define interior coordinate or interior harmonic basis. But then the Faber polynomial, I will explain it in the following slide. The Faber polynomial form a better basis than the monomial function g to the n. The Faber polynomial, by its name, I can figure it out, it's a polynomial, and it's, the order of Fm is m, defined by this generating relation. So W times psi prime divided by psi W minus C is expansion in terms of W, whose coefficient is a function of Z. And actually this function is polynomial order m, and the leading coefficient is 1 for each index n. And the Faber polynomials form a basis for complex analytic functions in omega. And there is several examples here. The F0 is just constant 1. F1 is first order polynomial. The leading coefficient equals to 1. And the F2, second order polynomial. And you see that the coefficient of F2 are A0, from A0 and A1. So that hold for general M. So for Fm, the coefficients are from A0 to A sub m minus 1. And the Faber polynomial has very convenient property, that is composition with psi has only one positive order term W to the m. So Fm composition with psi W equals to W to the m and has negative order term. And the negative orders are called the Gronsky coefficient. So you can understand that Faber polynomial is some polynomial order m, which has this property. I mean, combination with psi has one possible order term Wm. But this generating relation, by defining the generating relation, has better connection to the complex log function. But either way, you can define the same polynomial. And the Gronsky coefficient has this nice property. So K times CMK equals to M times CKM. And by multiplying square root M over K, the GKM is symmetric. That means GKM equals GMK. So this kind of symmetrization of Gronsky coefficient. Let me define this matrices. Capital C is a semi-infinite matrix whose entries are CMN, and G is symmetrized coefficient. Again, semi-infinite matrix with entries given by GMN. And we also need these diagonal matrices. Gamma to the plus or minus n has entry gamma to the plus or minus n integer numbers, and capital N to the plus or minus 1/2 is diagonal matrix whose entries are integer number square root or 1 over square root of integer number. So yeah, we define this C and G and diagonal matrices. They play an important role later. And from the generating a real equation for the Faber polynomial, we have expansion for complex log function. So log, when z is psi of w, the log of z minus z tilde equals to log w minus summation of 1 over n times Faber polynomial, the g tilde times w to the minus n. And when you have psi t minus psi w divided by t minus w, then the log function has expansion in terms of Gronsky coefficient divided by k. So the generating function relation is kind of derivative for this log expansion. If you see here, there is psi prime. So this is obtained from, you may obtain this by taking derivative for the expansion for log, or you can do the other way too. From this generating function relation, then obtain expansion for the log. And the Gronsky coefficient is related to Bowling upwards transformation. And Shepard considered the spectrum of the MP operator in relation to Bowling upwards transform, which is integral either interior of domain or exterior of domain. And the result my result is related to this transform for the exterior of omega, and that is integral of conjugate analytic function. So V is analytic square integrable, and we take V conjugate and then divide by psi minus c squared and take integral. And considered as all linear operator, this Bowling upwards transform has the same spectrum as that of the normal Poincare operator. So this is obtained by Shepard and Perfect Patina recently for a more general setup. And this Gronsky coefficient actually provides symmetric matrix expression for the Bowling upwards transformation. If we change the variable for the operator t omega till is this omega complement, then at the end, by changing the variable, you have a double summation of GMK. The GMK is symmetrized Gronsky coefficient and have a basis function psi m. So and there we use this expansion of log function in terms of Gronsky coefficient. So in this way, I told you that I explained that G and K equals GKM. So G is symmetric matrix. So this provides symmetric matrix expression for this T operator. And then matrix problem for finding the eigenvalue of T is just to solve matrix equation for a known coefficient V such that the multiplication equals to constant times the given coefficient B. So this so finding eigenvalue for this problem gives us the spectrum for MP operator when the domain is smooth. But today's object is to find the relation between component mapping coefficient with GPT values using the layer potential formulation. So differently from the T operator, we need to deal with the boundary integral operator. So now let me define basis functions for the density functions on boundary omega. So here H means the scale factor of psi. The psi is orthogonal coordinate defined by the complement mapping psi. And this scale factor is actually equals to the partial derivative with rho parameter and theta parameter. And define density function as kind of Fourier type basis. So exponential of plus or minus I m theta. And zeta tilde is divided by the scale factor. And rho zero is a parameter corresponds to the boundary of omega. And we modify the basis by square root of n. It's similar to the modification from Gronsky coefficient to C to the symmetric coefficient G. The eta is divided by square root of n, and zeta is multiplied by square root of n. And we know the expansion of the complex log in terms of Faber polynomial, and combination of Faber polynomial with psi has the expansion in terms of Gronsky coefficient. So this gives us the expansion for the singular potential. So singular potential for the Fourier basis has a polynomial inside omega, and the exterior, it has expansion in terms of exterior conformal exterior harmonic basis with the coefficient given by Gronsky coefficient. So singular potential admits this expansion. And also the MP operator has a series expansion with respect to zeta m and eta m. So zeta m and eta m are modified basis. So K star with zeta m and K with eta m has this different basis, but they have the same quotient, which we denoted by G MK, and this quotient is symmetric. So for C1 alpha domain, K star with this zeta m basis and K with eta m basis has the same symmetric matrix expression. So we can understand it as a way of symmetrize the Riemann-Poincaré operator, but with a different basis. With the different basis has the same matrix expression, and the matrix is symmetric. One application of this matrix expression is the decay estimate for the Riemann-Poincaré operator eigenvalues. When domain is C1 alpha, then eigenvalues are, the K star has only eigenvalues that decrease to 0 as index increase. And for analytic function, there's decaying is result, and also for CP class case, there's result. And with my former student, Chung, what we showed that for the class of C1 plus P alpha, then lambda K decays like, K to the minus P minus alpha plus 1/2. And the result is just obtained from this matrix expression and previous known result on the Gronsky coefficient decayness. Just combining that, we have this result. And another application is extension of Eshelby conjecture. Since we know the singular potential of the basis functions expression in terms of Gronsky coefficient and also expansion for the Riemann-Poincaré operator, we can understand the relation between the shape and the solution U in a more explicit way. So Eshelby conjecture is about ellipse, and when the applied field is first order polynomial, and then the induced field inside the inclusion is uniform. I mean, it's a first order polynomial. And actually the relation can be extended to higher order case. And here n equals 2 means psi has terms up to -2 term. So when the psi has just up to -1 order, then it gives us an Alice. When it has a -2 term, then I say that the shape is order 2. And for that case, there is a basis of apply the entire polynomial of order 2. So for that second order loading function, then induced field is uniform inside this order 2 shape. And that relation also holds in general for high order n2. So for order n shape, then the uniform field happens with h of order 3. When n is 3, when is n is equal to 4, so the omega is domain of order 4, then the applied field should be also polynomial of order 4. Now, let me also define complex contractility GPTs. So this is a combination of small m sub alpha in a way that it's related to complex polynomials, it's the case. So by definition, n, the GPT n is boundary integral with complex polynomial g to the n times lambda identity minus k star inverse and derivative of Pm. And the second type of GPT, we take the conjugate and also define infinite matrix N1 and N2. Now let me introduce Faber polynomial polarization tensors, in short, capital FPTs. And these terms are defined in terms of Faber polynomial instead of Zn. Then the same, almost same formula, but with Faber polynomial. And FPTs, it has expression in terms of GPTs. And Faber polynomial is polynomial order n, and the leading term is 1. So when you take the quotient, the diagonal entry is constantly 1, and it's lower triangular matrix. And it has, Faber polynomial polarization tensor has expansion in terms of GPTs, and using the matrix P, the F1 is P times N1 PT, and F2 is P conjugate N2 times P transpose. And since P is invertible, the GPT of first type is P inverse of FPT first type times P transpose inverse. And a GPT of second type is P conjugate inverse times F second type times P transpose inverse. So the FPT and GPT have this relation. And let's go back to the inverse problem. So from the definition of Faber polynomial and its expansion in terms of Gronsky coefficient, what we obtained is Faber polynomial polarization tensor is equal to constant times n times CMN, the Gronsky quotient, plus constant times n times 1/4 minus lambda squared times Gronsky matrix C times lambda square identity minus matrix defined by Gronsky coefficient inverse. And the second type has a similar expression. So in this case, the first term is simple. We just have index times Grensky quotient and index n times delta function. So you can easily find that when lambda equals to plus or minus 1/2, the second part is 0. So in this extreme case, then F1 has simple expression, F2 has simple expression, and in particular, F sub M1 of first type is 4 pi times m times am. So that gives you expression am in terms of FPT, and then the relation for F sub 1, and you get gamma square, and gamma is conformal radius, and A0 is determined by the third relation. So for piecewise C1 alpha domain without constant Son's boundary with extreme conductivity, from this relation in terms of Faber polynomial, and the Faber polynomial has expression in terms of GPTs. So by combining them, we get this explicit formula. And this is collaboration with my former student Che and my student Kim, and also Professor Joan Helsing. So for the extreme conductivity case, we get this explicit formula. And the last one, you may worry about that the PMN also rely on the shape of omega, but since AM is uniquely determined by the lower order terms, and this right hand side is fully determined by only using the GPT values. Now the remaining question is how to generalize this result to arbitrary conductivity case, because we got a nice formula for lambda equals to plus or minus 1/2, because this, the second part equals to 0 for the extreme case. But when lambda is other value, then it's not trivial to get information from the first relation and the second relation. Yeah. Then we got an idea that since this problem part is the same, the first type of GPT and the second type of GPT has expression, and they have different matrix factorization, but with the same factor that involves the lambda. So we got this idea that define n1/2 as the first time GPT times the second time GPT inverse. By doing that, this lambda involving part is canceled out, and modify GPT to using this n1/2 matrix. Then the tilde matrix is a generalization of the original GPT, because when lambda is plus or minus 1/2, they are equal. And by defining this tilde1 and tilde2, the n tilde 2 has this relation, which is the same equation for the original GPT, except that now we have this constant multiplied, and that part equals 1 when lambda is plus or minus 1. So this relation, this equation 3, is a nice generalization of the factorization of the GPT for the extreme case to the general case. And yeah, as we did for the extreme conductivity case, the relation, this relation provides us expression for component mapping coefficient. So the second part is exactly same as extreme conductivity case, except that now we use the modified GPT values. And the first part, for the extreme conductivity case, I assume that we know the sigma value. And now, instead of assuming the sigma value, now we can use this first equation. And the right-hand side also depends on lambda, but by numerical computation, we can optimize the value such that the equation 4 holds. So find lambda numerically, and then as you know the lambda value, then the right-hand side is just a formula in terms of measurement value, because n tilde, the modified GPTs, are from the GPT values and GPTs are from multistatic measurement. So the right-hand side is fully determined by the measurement. So here is a numerical simulation. So the domain is this perturbed ellipse. So it is an ellipse with a corner, ellipsis corner, and the GPTs are numerically computed by Nystrom discretization, accelerated with all-CIP computation, thanks to Professor Joan Helsing. And if you see that by using GPT values up to order 2, then we just have an ellipse, equivalent ellipse, and having more values. And in that case, we have sufficiently many GPT values, then it catches this corner shape actually. And the lambda is 1, and using more GPT values that we can reconstruct the sigma very well. And so this is a result with random noise. And interestingly, the omega and omega tilde have the same shape, except that now the A0 and the location of the domain is now shifted. You know, if A0 is 0, then it's quite reconstruction is quite robust with the random noise. But when A0 is not 0, then you see that it's more sensitive to the noise. Because when we compute the coefficient by using this formula, A0 actually repeatedly appeared. So when there is a noise in A0, then it induces a difference in a higher order coefficient. So it's more sensitive to the random noise. Okay, thank you so much for your attention.
Thank you, Mikyoung. Are there any questions?
Can I start with the questions? But feel free to raise your hand or use the chat if you want to ask questions, and we'll be happy to unmute you so that you can ask your question directly. But in any case, thank you, Mikyoung, for your talk. It was very interesting. There is one point which wasn't clear to me about the Eshelby conjecture. In that case, you're looking for you're not looking at the elasticity operator, are you? Or are you just looking at the case of you're using symmetry to get back to something like conduction?
Yeah, this was just two-dimensional anti-plane lattice in anti-plane case, conductivity equation.
Okay, so there is no shear in this computation. Or,
exactly.
You're using gamma as the green functions, not the green function, not the green function for elasticity.
No.
Okay.
Just the two-dimensional conductivity equation.
I see. Okay.
Yeah.
Okay. And concerning these last pictures that you show, first of all, you showed a picture with a modified ellipse or perturbed ellipse with a corner. Does any of the development using this representation of the solution, can one do that for shapes which have corners?
Yeah, so I see that it has corner and ellipse that's perturbed to have a corner. So this works for C1 alpha domain and also for Lipschitz domain satisfying star shape condition. Yeah.
Okay. So it does extend to Lipschitz domain.
Yeah.
Okay. All right. And could you predict beforehand how many coefficients you would need to reconstruct to that is, do you have anything that tells you, well, if I compute up to the 10th coefficient in this expansion, then I recover the shape with so much precision?
We have this kind of explicit formula. So for the extreme conductivity case, the AM is from GPT up to order M. That is correct one. I mean, to correctly recover, we know how many GPT values to use, and then depending on the domain with higher large number for AM with large index M, then some shape with only lower small number of coefficient, then using just lower the GPTs and it gives it the full shape. So it really depends on the shape of omega, and definitely for the corner domain case, then coefficient decay slowly, then so really depends on the regularity of the boundary.
Okay.
I have a question. So Mikyoung, I guess the case of multiple inclusions, can you explain what the difficulties are there? I know that's significantly harder, but I don't really understand what the difference is.
So this the whole method relying on the expression of inclusion in terms of one conformal mapping. And that exists in general. We know the existence for simply connected domain. So that's the main restriction to apply this method to multi-connected domain.
Okay, but even if, suppose they were really close in proximity, lines.
Then we can use it as, then you're right. And approximately you can,
Okay, so that would be the way to do it if they're kind of right.
Yeah,
right?
I think
if
so.
They're close enough that you could approximate them as one, which you could.
But for that case, high order coefficient will not be good as simply connected one.
Okay.
Yeah.
Okay, thanks.